Hi, Spring fans. Welcome to another installment of Spring Tips. We're continuing our look at the groovy and grand world of GraphQL. In the last episode, we looked at the low-level GraphQL Java engine, but did so in terms of the Spring Boot starter that comes in Spring 2.7. In this installment, we'll continue our exploration, focusing on Spring for GraphQL component model. One of the most amazing aspects of Spring for GraphQL is the flexible way it integrates both reactive and imperative I/O styles. To hear more about this, let's talk to Spring for GraphQL lead Rossen Stoyanchev. You've probably heard that name a few times on the show by this point. He's been a guest on the podcast a few times as well. He's also in the code that you're using in production, and that's all but guaranteed. He's greatly improved or started and led the work to develop things like the RSocket integration in Spring, Spring MVC, Spring WebFlux, the Spring WebSocket support in Spring Framework 4 and onwards, and so much more. So, Rossen, what do you say?
In Spring 4 GraphQL, we've provided support for annotated controllers with controller methods that in many ways can be compared to a web controller that you would use in Spring MVC, except here we have query mapping, mutation mapping methods instead of request mapping methods. And in order to begin to understand how this looks, you can think of how in a web environment you would typically get a HTTP URL, and then the request mapping controller method is going to fetch some data from somewhere and return it, prepare the full response. In GraphQL, we have the GraphQL engine, and we are much more data driven, data oriented. There is the schema. And so the GraphQL engine is going to look at what fields are requested in a hierarchical manner, and then go through and invoke all the registered data fetchers, which in this case, we have the annotated controller methods that are mapped to individual fields. And it all kind of comes together through the GraphQL engine, selecting what needs to be returned, not necessarily everything, while we take care of fetching the data, sometimes overriding on a very specific level. You might be kind of hierarchically a couple of levels down. Instead of the level above returning the whole object, you might override just one individual field and fetch it from somewhere else, maybe from a remote service or from a different database. There's a wide range of options in terms of where the data can come from in the backend, including from memory. The controllers, just like in a web controller, the data controllers here have flexible method signatures. And that means that there's a range of different arguments that are supported that can be passed in. And there's also a flexible choice of return values. So one option would be to return the actual data, which of course would mean that that has to be fetched synchronously. But you can also return this data asynchronously by returning a reactive mono or reactive flux. And this is important because if you think about the data graph and multiple fields being fetched, GraphQL Java will do that in parallel if the actual data fetchers are themselves asynchronous. So if we return flux or mono, that allows for that data to be fetched in parallel while the GraphQL engine assembles that and returns the combined data.
That's pretty cool, right? It only stands to reason that the Spring for GraphQL project would feature first in flight integration with reactive and imperative programming styles, because who knows more about either of those than Rossen Stoyanchev. There's an interesting possibility here, friends. You can write GraphQL code that sits on top of whatever web runtime you like and fully maximize your use of that web runtime without having to switch. I love this. Now, for our purposes, in most of these videos, if not all, we're going to be sticking to reactive programming because there are some implied benefits there that you just get for free by using reactive programming, as we'll see in the next several episodes. In the last video, we looked at how to do basic queries with the low-level data wiring configure. This time, we're going to moving up from the GraphQL Java project and moving to the component model that Spring for GraphQL provides. So let's return to start.spring.io, and this time we'll create a new project using Spring Boot 2.7 just as before. And we're going to call this queries, just because that's the thing on which we'll focus on this one installment. We're going to use the reactive web support, and we're going to use the soon to be 2.70 released Spring Boot starter for Spring for GraphQL. So let's hit generate, and we'll open this up in our IDE as always. All right, here's our brand new application. And as always, when you write these kinds of applications, when you write code that uses GraphQL, it pays to think about the schema. So what we're going to do is we're going to create our schema folder here, source, main, resources. I'm going to create a directory here called GraphQL. And we're going to create a new file here, and we're just going to call it queries.graphqls, yeah? And we're going to define some very simple types. The first and most obvious of which is a query. A query is, as I said before, a root type. It's a common type. It's a well-known type that all GraphQL projects will probably have. It's the thing where people who are looking at your API will first look to find out about how they can read data in your system. And so we're going to create a few fields. We're going to create a few fields that return data. Let's just start with something super, super simple. Just hello. It's going to return a string. Okay, so it takes no arguments and it returns a string. We have to turn that into a controller. So we'll say class, greetings controller, and we'll start with @query mapping. Okay, because this is a type in a query. All right, so we're going to say string hello world. All right, so that's the equivalent implementation of that. We want to test this out. Let's go ahead and start the application up. So we'll say graphical enabled equals to true, and then just start it up. Yeah. Okay, so the application's up and running. Localhost graphical. All right, we're going to do query hello, and we get the response we expect back. So that's pretty straightforward, yeah? We've got a handler method that responds to responds to queries that you can be resolved as fields in the top level well-known root query type. Okay, now behind the scenes, this query mapping is actually a specialization of a more general purpose annotation called schema mapping. Okay, so we could actually write this like this. We could say type name equals query, and the field is equal to hello. All right, that's semantically the same thing. When we use query mapping, we derive the name of the field from the method name, and we assume that the type name is equal to query. Well, you can use schema mapping, but you don't need to use it for the well-known types like mutation, like query, etc. Or subscription, for example, because for those, we have annotations. In this way, it's very similar to the relationship between @request mapping and @get mapping and @post mapping and @put mapping and so on, right? So there's specializations of a general purpose annotation that you're free to use if you like. They're just slightly less verbose. They're more expressive. Okay, so we've got our very simple hello endpoint. Let's try something with a parameter. Yeah, so we're going to say @query mapping string hello with name. Yeah, and the argument will be string name. So we'll say return hello name. Voila. Now we have to add this to our types. Very easy to do. So hello with name string, and it'll take an argument, and the argument type is it's a name and it's a type of string. Yeah. So if we restart this, go here, refresh, query, hello with name, it auto completes, it wants the name. So we'll say world, and voila, there's our hello world. Okay. So hello Spring fans. There you go, hello Spring fans. So we now have the ability to parameterize our fields, to send arguments into them, to filter, to support the resolution of particular bits of data. Okay. Now let's suppose we want to return something more interesting than just a regular string. So we say record customer, integer ID, string name, and we can return a single customer. We could say customer by ID. ID is ID, and it'll return a single customer. And the type for customer, of course, is just ID, name, string. All right, so that's just a very simple customer. Let's implement that here. So we say at query mapping, customer by ID, argument, integer ID, return, just whatever. So ID is ID, and it'll be math.random greater than 0.5, A, otherwise B. All right. So we're using customer by ID as a field. It's taking an argument. We're returning a semantically more meaningful type called a customer. Let's go ahead and try that out. So refresh this query, customer by ID is 1. Now you notice that if I just try and leave it like that, it won't work, right? If I try and execute, it'll autocomplete one subordinate field, because it's strings are scalar. They're simple flat like values. There's no properties within that you care about that you can decompose it further. Whereas a customer has fields. It has interesting fields like a name and an ID and so on. So you have to specify what fields you want. So I want the ID at a minimum, and I want the name. Very good. So I say customer by ID, and the result is customer by ID with ID 1 and name B. And if I'm just switching back and forth between A and B here. But the point is, the result is basically the same. It works exactly the same way as before. All you have to do is create the endpoint there. Now, what if I want multiple values? Well, of course, here I can do query mapping, and I can return a collection of customer, right? Customers, return, and let's just say we have a list here, private final list of customers, list.of, new customer 1A, new customer 2B, yeah? So there's this. Good, and we can just return that list. This.customer list. That'll work. That's just fine. Obviously, you in a more general purpose sort of application, you'd probably talk to a database of some sort, right? You wouldn't just return hard-coded data in memory in your Java code. But you can imagine talking to Spring Data JPA or whatever, right? Here, I'm just returning a regular customer. So let's define that. We'll say we have a more than one value. So the type is wrapped in square parentheses, customer, yeah. Let's go ahead and restart this. Okay, and here, refresh. Okay, customers, and voila. So if I do that, and I want the name, or I can do this. So I get the data back as individual fields, but I get multiple records, which is great, right? Now here, I'm returning all the data at once. I have all the data in memory, but what if I was trying to return data from a reactive service, right? I'm talking to a reactive database like R2DBC or the reactive Neo4j implementation or the reactive MongoDB implementation or whatever. Well, there I can just return a flux if I like, right? The component model doesn't really care what you return. Is it'll work with you on whatever. So returning a reactive stream, if you use the web client, the reactive web client, and you make a call to another service and you get the response back, that'll be a reactive publisher, to be a flux or a mono. So here I'm just returning a flux, as you might get back from talking to R2DBC via Spring Data R2DBC, or to MongoDB or Neo4j or Redis or Google Cloud Spanner or Microsoft Azure, Cosmos DB or whatever implementation that provides a reactive type like a publisher, a mono, a flux. That will work just fine as well here. So we can rework this. Let's just restart it to see what happens. Okay, so customers, same exact result. There we are. Okay, that's working fine. Great. Now, what if my customer had a related type? Let's say that my customer type had an account object, okay? And so I'll go down here, I'll say type is equal to account and ID, and whatever, it doesn't really all that much matter. So let's just go ahead and synthesize that. And so we'll create another endpoint, and here we can actually use our schema mapping. So the type name here is customer, but what we're returning is an account object. Okay, so we need a record account integer ID, and we'll say account. Now, of course, in order to return the right account for a given customer, I need a pointer to that customer, because that's, if you think of it in terms of like an aggregate, the root is the customer, and then for the account, I need a reference to the customer to know which account to look up, right? So I can say customer, and here I can return a new account. I'll say, okay, new account is equal to customer.id, whatever, just as a simple example. Okay, restart. Notice that I didn't specify the field here. I just specified the type name. I could have, but I don't need to, right? Okay, query. And we're going to use customers. And there I've got ID, name, and of course account. Well, account, of course, in this case, in turn, has an ID. So I can bring all that back. So you can see there I've got customers, and each customer has account data. And I'm getting that account data for each customer. It's calling this schema mapping method, right? And so even though behind the scenes, this could have come from one database and this could have come from another, even though they could be completely different sources, or they could be the same thing. Obviously, it could be just you're talking to a JDBC in both of them. Even though that's true, well, not JDBC if you're using Reactive, but something you can use. This could be a mono of account, and then you could use R2DBC, if you like, or you could use JDBC if you got rid of the reactive types. It would just be very seamless either way. The point is, Spring for GraphQL doesn't care. It'll give you the ability to invoke these handler methods to resolve parts of the object graph on demand. Okay, so here we're giving the client the impression that this data is related. I ask for the customers and I get back the name, the ID, and the account information, right? Which is great. But they're not related. They actually could be on totally different microservices. They could be in different places. I think that's one of the most powerful parts about this whole arrangement, is that we can use reactive types and non-reactive types in the same code base. And if we're using reactive types and we're actually calling different services, different hosts and ports, well, that implies some latency. So what you want is to make that as efficient as possible. In this case, we've got a bit of a not great case, right? We're calling to get all the customers, but for all the customers that we get, we also get back an account, and that implies an n+1, right? I'm going to get how many customers do we have? 2. We have 2 customers. So for each customer, it's going to invoke this account method, passing in the root of the aggregate, and I'm going to resolve the account, and that implies that I've got 1 call to get both customers, and then 2 calls, 1 call each for each customer to get the account for that customer. So that's a total of 3 network calls. Now, if I had 10 customers, then by definition, I would have 11 total calls, 10 for each account for each customer, and 1 for the total of all 10 customers, right? And that's not great. We're going to see later how you can get around that. But in the meantime, one thing you should be aware of is that these reactive types, because they are asynchronous, they will actually execute concurrently. So in this case, it doesn't work, right? Obviously, it's just in memory. But let's say you actually called let's say you called R2DBC, and R2DBC is using non-blocking I/O, and you're using reactive types. Okay. In this case, because the return value is a reactive type, Spring for GraphQL, the GraphQL engine underneath the hood, and Spring for GraphQL with its adapter code on top of it, is going to do a for loop basically for each of the customers in their first response, and then it's going to call the account method, and it's going to expect the response to come back. Well, if the response actually has to make a network call and call a database, then you're effectively serializing all of the calls. But if you're using reactive types, then it returns immediately, doesn't it? Because what you've got is more like a promise. Those promises will get resolved, but they all get resolved concurrently because you've obtained the promise for all 10 customers all at once. It's just instantaneous, right? I call account, I get a promise for an account instantaneously. The resolution of that account takes a little bit, but that's not the problem here, right? The point is I've teed up all 10 of these network requests and I've launched them on whatever threads the scheduler for my reactive runtime is using. And in theory, I'm getting my results concurrently. I'm making one request for all the customers, but I'm making 10 concurrent requests for the individual accounts, as opposed to what I would get if I were using non-reactive types, if I were using just account, or if I was returning just a single account without wrapping it in that mono, right? In that case, I would have to wait for the result to be resolved, and then I would return that from the method. So it would get to the first account, call the database, wait for the response, then call the second method, call the second account, call the database, get the response, and so on. So that would be serialized. So using reactive APIs here isn't just convenient, and it's not just nice that your GraphQL engine can support both reactive and non-reactive flows, but in this case, you actually get some really nice performance benefits if, for whatever reason, you can't further optimize it through something like batch mapping, which we'll look at in just a bit. In this video, we looked at queries, and we looked at how to read data and how to seamlessly mix that data into one object graph so that the client is unaware of the origin of the data. However, we ran into one problem. We have an n+1 sort of scenario. In the next episode, we'll look at how to use batch mapping to optimize your queries so that you don't incur this unnecessary n+1 cost.